My name is Dan Oak and I'm a student at Athabasca University, and I'm currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following any of the videos I've been posting in the course forum so far, you'll know that I'm going through the SparkFun Inventor's Kit Guide, and I'm showing you how I've completed the projects and the associated coding challenges with those projects. So on the course forum so far, I have videos posted showing me completing projects 1 through 4, along with all of the circuits and coding challenges with those projects. So I would highly recommend you watch those videos before today's video, simply because some of the concepts I'm going to be talking about today, I'm just going to briefly mention and maybe go over a little bit, but I'm not going to go into great detail because I've already done that in previous videos. However, if you do feel comfortable watching today's video on Project 5, if you do end up having any questions, feel free just to post them on the course forum and I'll be happy to answer. So in today's video, I'm going to be demonstrating Circuit 5A from the SparkFun Inventor's Kit, which focuses on controlling a motor using a motor driver with the SparkFun breadboard. We'll start by discussing the circuit setup. The components we'll be using include a motor driver, the DC motor itself, and a switch, which I'm going to use to start and stop the motor. The motor driver has 3 important pins, so 2 input pins for channel A and a PWM pin for channel A, and those are going to be connected to pins 13 through 11 on the Arduino. And the motor speed is controlled using the PWM pin. So pulse width modulation pin, where I'm going to set it using values between 0 and 255 to control the motor speed effectively. Next, I'll explain the initial Arduino code setup, which begins by initializing the pins for the motor and the switch and configuring the serial communication for input. In the loop, I'll show how we read the motor speed input from the serial monitor and what happens when the switch state is checked. The motor spins only when the switch is turned on. I'll walk through the spin motor function, which determines the motor's direction based on the sign of the speed input. So if it's a negative sign, the motor will spin in one direction, the reverse direction. Vice, if it's a positive sign, the motor will spin in the forward direction. And we'll adjust the controls accordingly. Now let's transition to my version of the code for the coding challenge, which introduces multiple input methods and RGB LED feedback. In this version, I've added functionality so that the motor direction can be controlled by a switch, and a button can turn the motor on and off, meaning the motor will be turned on when the button is depressed, off when it's not depressed. I'll also use a photoresistor, which can regulate the operation of the motor based on light levels, and I'm going to have an RGB LED that's going to show the color based on the motor speed, transitioning through the colors to indicate changes, which brings a visual component to my project. Basically, the RGB LED is going to light up in various colors as the speed changes. I'm also going to demonstrate how to navigate through the different modes, the different coding challenges, using a button, and adjust the motor speed dynamically through the serial monitor. Throughout this video, I aim to highlight not just how to wire the circuit, but also the coding practices behind Arduino programming, demonstrating real-time responsiveness and user interactivity. Finally, we'll test each feature in real time, ensuring everything works as expected, which is not often the case in electronics, while I discuss the design choices of my code, such as using Boolean flags for state changes and debounce logic for button presses, while emphasizing good programming practices that ensure code readability and functionality. And as always, I encourage all Com444 students to try these coding challenges on your own. And if you have any questions, please post them to the course forum and I'll be happy to answer. So thanks for watching, and let's dive into the demonstration. So for anyone who has followed the videos I posted before, you'll know that I typically go through the SparkFun Inventor's Kit Guide, but I don't read it in its entirety. I just kind of go through the highlights, and then I go through, walk you guys through my code. So we're going to start like that. So for Project 5, there's 3 different circuits. We're going to be focused on Circuit A today, so motor basics, and then I will have videos showing me going through Circuits B and C, where we're going to discuss remote control robots and autonomous robots. So Project 5. Let me just send this down a little bit. So Project 5. Robots are one of the most iconic and exciting electronics applications. So in this project, you're going to learn about DC motors and motor drivers, which are a major component of robots. I mean, we like robots to move. So you're first going to learn motor basics. That's in today's project, so Circuit 5A. And then in 5B, we're going to talk about controlling a tethered robot that's attached to the computer by sending commands over the serial monitor. And then and that's circuit 5B. And last, in circuit 5C, we're going to make our robot autonomous using a distance sensor to avoid obstacles. But that's what's to come in Project 5, where we're going to be using all these components, these new concepts, and we're going to learn a lot of different stuff. So throughout Project 5, we're going to be discussing the TB6612 FNG motor driver, and that will be discussed today. We're going to be using a switch, a DC gear motor, again using today, as well as a wheel. So the wheel is not going to be used today, but all of these things are. We're going to be discussing input voltage, integrated circuits, H-grid motor drivers, ASCII characters. We're going to be converting strings, and we'll be talking about autonomous vehicles. Again, that's not today. The things today are really the H-bridge and the ASCII characters. And then, so what we're going to learn is we're going to learn how to use a motor driver. We're going to create a remote-controlled robot and how to build a robot that uses sensors to react to its environment. So today, it's just the motor driver. So, Circuit 5A, motor basics. So motors require a lot of current. That's the main thing we're going to learn today, one of them. So you can't drive them directly from a digital pin on the breadboard, at least not effectively, which is why we're going to use what's known, instead we're going to use a motor controller or a motor driver board, which is this component right here. And the other components we're going to use is the gear motor. You would have got these in the kits, and these are also fairly ubiquitous if you've got in any other Arduino kits online like I have. These are the standard motors you get in those kits. We're going to use a switch, which is different than a push button that we've been using before, and some hookup wires. So the new components we're going to be using, as I said, switches, which controls the openness or closeness of an electrical circuit. So just like momentary buttons, which we've been using so far, a switch only exists in one of two states. You can either have the circuit open or closed, depending on the position of the switch. However, a switch is different than a button in that it will stay in the position it was last in until it's switched again. So, if you switch the switch to, very confusing, to, the right here, it's going to stay there until you physically move it back. Whereas a button, you press it and then it immediately goes back. So there's some persistence with switches. The motors in your Inventor's kit, there's two main parts. There's a small DC motor, which spins quickly, which is this part, and then there's a plastic gearbox that gears down the output from the hobby motor so that it's slower but stronger, allowing it to move your robot. So if you're taking Comp 444 and you've read the textbook at all, you'll have went through a chapter talking about torque and gear ratios. That's what's happening here. So we won't discuss that today. That's for another video. But suffice to say that if we were using this part of the motor, the DC motor, this spins really quick. It's not very powerful, but it spins really quick. So you would attach things like a fan or a flag to this. Whereas the gear, the plastic gearbox gears down the output from the motor, making it a lot stronger. And so you could use it, you could attach like a wheel or something to the plastic axle here, and it would be stronger. And that's what we need when we want to move a robot. We need the wheels to have enough torque to physically move the robot around. We're also going to be, our main thing we're going to be discussing today is the motor driver, specifically the TB6612 FNG motor driver, why we're using motor driver? Well, if you switch the direction of current through a motor by swapping the positive and negative leads, the motor will spin in the opposite direction. So a motor is polarized, but a little different than polarized in the sense of LEDs, where if you put current through it the wrong way, it just won't work and will damage the LED. Switching the current, the direction that the current goes through a motor, just changes the direction the motor spins. So a motor driver allows us to control that via a microcontroller, as opposed to physically just plugging the wire leads from a motor and plugging them differently into the power. So I've kind of mentioned up here again, motors are polarized components, but not in the same way an LED is, which will be damaged if the polarity is reversed. A motor simply will spin in the opposite direction. So the TB6612 FNG motor driver takes the commands for each motor over 3 wires. 2 wires control direction. Those were the input wires, AIN 1 and 2, and 1 controls the speed. That was your PWM pin. And then it uses these signals to control the current through the 2 wires attached to your motor. And controlling the current through the 2 wires controls the direction the motor spins. Another new concept we're going to be talking about today is voltage in. This circuit uses the VIN pin found with other breadboard power pins. And the VIN pin outputs a voltage that varies based on whatever voltage the breadboard is powered with. So if the breadboard is powered through the USB port, which we've been doing thus far in the course, just plugged into your computer, then the voltage on the VIN pin will be about 4.6 to 5 volts. However, if you power the breadboard through the barrel jack, highlighted in the picture here, so if you're using the barrel jack and an external battery pack or something like that to power your Arduino, then, and this is the VIN pin by the way, then the VIN pin will reflect that voltage. So for example, if you're using a 9-volt battery pack, then the VIN will be 9 volts. So, and as you can see here, the breadboard barrel jack is rated for 7 to 15 volts. So do not exceed this range. So you want a voltage in that range. And definitely never exceed 15 volts. You'll end up damaging your board. Another concept we're going to be talking about today is integrated circuits, ICs, and breakout boards. So an integrated circuit, IC, is just a collection of electronic components. Resistors, transistors, capacitors, etc. You name it. It's just all stuffed into a tiny chip and connected together to achieve some common goal. So they come in all sorts of flavors, shapes, and sizes. The chip that powers the breadboard, the Atmega 328, which we mentioned in the very first video, is an IC. So if you look at the breadboard here, the Atmega 328, that's an IC, and that's really that's the brains behind the our microcontroller. And similar to that being an IC, the chip on the motor driver is also an IC, the TB6612 FNG. It's another IC. Integrated circuits are often too small to work with by hand, so to make them breadboard compatible, they're added to a breakout board. So the chip might be a certain size, but we don't actually, that's not all the actual circuitry. A lot of it's just wires and internal, just so that we can work with them. This is the motor controller, a picture of it. This is just talking about, again, motors are polarized, so they will still work if the two connections are reversed. So if you reverse the positive and negative lead, everything will still work. It'll just spin in the opposite direction when hooked up backwards. So for our purposes, let's just think of the red wire as positive and the negative wire as the black wire is negative. But yeah, if you mix these up and put them the opposite way, it just spins backwards, and that's kind of what the motor driver uses to control the direction that the motor spins in. So meet your motor controller. So this is the TB6612 FNG motor driver, and it looks complicated, but it's not that bad actually when you look at it. So motors require more current. This is why we need the VIN voltage is needed. We can't just run it off of our 5 volts. Motors take a lot more current than our microcontrollers are able to provide, which is why our microcontrollers have that external barrel jack capability where you can plug in a battery pack and use VIN to power something else. We can use the microcontroller to control things, but the power actually controlling the motor comes from VIN. So most ICs have polarity and usually have a polarity marking in one of the corners, just indicating what direction you should be plugging it in. This is the pinout for the motor driver. So briefly we'll just discuss. So that we've got, when you ever see A here, there's 2 channels. You can technically, you can control 2 different motors with this single motor driver. So everything's kind of in double. We've got a PWM pin for channel A and inputs 1 and 2 for channel A. And then we have the same thing for channel B if we had a second motor. A PWM pin for channel B along with inputs. We have a standby pin we'll talk about, and we've got a couple common ground pins. 1, 2, 3 here. They're all connected together, common ground. And then the inputs for channel A, then we have the outputs. So output 1 and 2, which would be the positive and negative lead of the your motor for channel A. And if you had a second motor hooked up for B, then these would be the outputs for B. And then we have our voltage in pins. So VM is the motor voltage. This pin is where you're going to hook up your VIN, your voltage in, which is going to be the power coming from your microcontroller that's associated with an external battery pack or something like that, that 7 to 15 volts. Whereas VCC is just powered via your microcontroller, the 5 volts from your microcontroller. So this VCC controls the logic for the motor driver, which is running off 5 volts, just your regular Arduino logic. Whereas VM, that's the voltage for your motor, so that's your 7 to 15 volts. This just explains the pins in more detail. Again, VM is your motor voltage. You want to provide, it's where you provide power for the motors, which can be anywhere from 2.2 volts to 13.5 volts. Your VCC, that's your logic voltage. It's the voltage to power the chip and talk to the microcontroller. Again, it's going to be between 2.7 and 5.5 volts. Ground, it's a common ground for all the ground pins are connected together, the 3 of them. And then you have for channel A, so for one motor, you have your 2 input pins, input 1 and input 2 for channel A. And same for B. You have, so channel A has an input 1, channel B has an input 1. Channel A has an input 2, channel B has an input 2. And all your input pins are doing is they're determining the direction that your motor spins in. And then you have 2 PWM pins, so PWM pin for A and B. And again, the PWM input controls the speed the motor spins at. And then you have your output pins, again, for channel A and B. That's actually connected to the motor. Here's the pinout guide, as you can see, or the schematic rather. So, as you can see here, the positive rail and ground rails on this breadboard, both sides are connected together down here via these connections, and they're ultimately connected to 5 volts and ground of the microcontroller. And then VIN, which is, again, we'd have an external battery pack hooked in through this barrel jack that's between 7 and 15 volts. It is outputting at the VIN pin, which we're using the VIN pin to connect to the VM, that's Victor Mike pin, of your motor driver. Whereas your VCC is connected to the 5 volts because it's connected to the power rail of the breadboard, which is ultimately connected to 5 volts of the microcontroller. We're not using 2 motors today, or correction, we have 2 motors hooked up, so we have both. We've hooked up the inputs and PWM pins for motor A, and we've done it for motor B as well, but we've only got 1 motor hooked up, so B is not being used at this point. They've shown it hooked up here, but that's for this particular circuit, it's not necessary. That'll come into play in circuit 5B and 5C, but for this circuit, we're only using 1 motor. So you can see we've only hooked up output to the channel A output 1 and 2, which is just hooked up to our motor. As well, we have the switch hooked up here. So the middle terminal, or the middle pin of the switch, hooks to ground, and then either of the other pins, the edge pins, hook up to any digital pin. So again, make sure that you don't have both pins hooked up, both external pins hooked up, like you don't want 1 to 7 and then the external pin hooked into ground. It's the middle pin that gets connected to ground, and then either of the exterior pins connected to a digital pin. One other thing I'll mention, I keep saying we have a PWM A pin and a PWM B pin, so PWM pins, pulse width modulation pins, for channel A and channel B if you have 2 motors. So those obviously have to be on PWM pins. So in the Arduino there's 14 digital pins, 6 of them are PWM, and they're indicated by this little tilde symbol beside the pin number. So 3, 5, 6, 9, 10, 11, those are all PWM pins, and you can see the pink wire coming from PWM A is connected to 11, and the green wire from PWM B is connected to 10. So they're both connected to PWM pins. And then so when you have this circuit hooked up, this is kind of what you should see here. So, and you're going to be able to flip the switch and the motor will spin at the speed set by the motor speed variable. The default is 0 when you first start, just for safety purposes. And then we're going to open the serial monitor and we're going to type any number from 30 to 255, or from -30 to -255. The negative indicates that you want the motor to spin in the opposite direction. And then you're just going to press enter. And then changes in speed will be hard to notice, but there will be changes. And you're going to send 0 to stop the motor. You want a speed of 0. So that's the general program. That's not fully what we're going to be really discussing today, but that's the Circuit 5A program when you just take the code that you would have got from the SparkFun Inventors Kit guide or the website and just upload it into the circuit like this. That's what's going to happen. Flipping the switch is just going to turn the motor on and off, and you're going to set the speed based on the serial monitor input. And this is the program overview here. You're going to check if there's a command has been sent to the serial monitor, and then you're going to set the motor speed based on that number from the serial monitor. And then you're going to check the switches on or off. If the switch is on, you're going to drive the motor at the motor speed. If the switch is off, you're going to stop the motor. The code to note in the Arduino code that comes from the SparkFun Inventors Kit guide or the website is the parseInt function, which retrieves integer numbers from the serial monitor. And then it returns the value of the number that it receives so that you can use it in a variable. So if you've watched any of my previous videos, you'll know that we've discussed the parseInt function before, which is really a really simple way just to get integer values from the user. I think in the code that I'm using for the coding challenge, I do it a little more complicated because I'm using a serial.read function which returns character values, and then I use a little bit of clever coding that's kind of common in the Arduino programming world to convert character values to integers. I do use parseInt a lot in some of my other videos, but I go back and forth between parseInt and this just to keep the practice up on both of them. And although the method I'm using today is a little more complicated than just using parseInt, I'm using it just to get that practice. But I'll discuss that in detail when I show you the code. And then we're going to also use the serial.available function, which basically checks how many bytes of data are being sent to the breadboard via the serial monitor. If it is greater than 0, then a message has been sent. And then we can use an if statement to run code only when a command has been received. So basically what that means is we're going to, in our code, we're going to use an if statement to say if serial.available is greater than 0, meaning there's anything in the serial monitor available, then we're going to do something. That means there's data available in the serial monitor, and we're just going to do something in the code. So that's what the basic code does. But we don't like the basic code. We want to do coding challenges, a little more dynamic, fun stuff. So the coding challenge today, there's 3 of them. We're going to replace the switch. We're going to place the basic functionality of the switch, which just turned the motor on and off. And now we're going to use the switch to change the directions that the motor spins in. So the position of the switch will change the direction that the motor goes. And then we're going to replace the switch's functionality, which just turned the motor on and off, with a button. So now the motor is only going to turn on when you're pushing the button down. So when you're depressing the button. And then we're also going to replace the switch with a sensor. So the motor is going to be activated by another sensor, in this case a photoresistor, which we've discussed and used a lot in our previous videos. So that's what we're really going to be discussing today, the coding challenges. I'm quickly going to go over the code, the basic code, but for the most part, we're going to go beyond that pretty quick. So the basic code is this. The basic code that you can download off of the SparkFun Inventors Kit guide website and get all the circuit diagrams and instructions, basically which we just went through, is like this. It's got some constants showing you the 3 pins associated with the motor, your input pins control direction, your PWM pin controlling the speed, the switch pin is on pin 7, and a motor speed variable controlling the speed. That'll be between values of 0 and 255. In setup, we call the pin mode function, setting up our switch pin as an input, and we use the input pull-up argument passed in, which basically uses the internal pull-up resistor, the 28 kilo ohm resistor associated with our microcontroller, so we don't have to use a physical resistor. We set up all of our motor control pins as outputs, because they're all outputs, our direction control and our speed control, and we set up communication with the serial monitor at 9600 baud rate, and we just output, hey, enter a motor speed from 0 to 255. In the loop, we're constantly just checking if there's anything available, meaning did the user put anything in. If they did, we're going to use that parseIn function to set the motor speed variable to whatever they typed in. So this is going to grab whatever they type in and set it to motor speed, assuming that they've typed in a value between 0 and 255 that can be parsed as an integer value. We're going to output the motor speed to the user so they know what they're running at. And then we're going to constantly be checking if digital read of pin 7, which is the switch pin, which is weird they used pin 7 considering they created a variable up here called switch pin. So typically you'd create a variable or a constant so that you could use it, but they've just created it and not used it, which I find somewhat funny. I guess they probably used it up here in pin mode and then didn't bother using it again. But typically you would use that everywhere. It's always better, I've mentioned this a lot in my previous videos, always better to use constant values than magic numbers. Like we all know what this, it's fairly simple code. We know that pin 7 represents the switch pin, but it would have been better just to put switch pin here. But anyway, we're reading that switch pin, and if it equals low, meaning the switch is on, then we're going to call the spin motor function passing in motor speed, and we're going to spin the motor at that speed. Else, meaning it was high, we're going to turn the motor off, passing a 0 to it. Here's how the spin motor function works. Again, it takes in a single parameter of type int, motor speed, and it doesn't return anything. And if the motor speed is greater than 0, meaning if it's positive, then we're going to call digital write on the 2 analog pins, setting the input 1 pin for channel A to high and input 2 pin to low. And that's kind of the convention that the motor driver uses in order to tell the motor to drive forward. Input 1 is high, input 2 is low. Else if the motor speed is less than 0, meaning if it's a negative number, we're going to do the opposite. We're going to set channel A's input 1 to low and channel A's input 2 to high. That indicates to go in the reverse direction. Else, meaning it wasn't a positive number or negative number, well, it can only be one other option, 0. We're going to set both analog, we're going to set both channel A inputs to low. And that indicates just to stop the motor. And then after we're done all that, controlling direction, all this part is control the direction so far that the motor spins in. Then we're actually going to control the speed by calling an analog write function, passing in our PWMA, that's our constant representing the PWM pin, and then we're going to pass in the motor speed. Now notice we're calling an absolute function here. This is a function associated with built into Arduino in the math libraries that allows you to pass in a number, and it gives you the absolute value of that number, meaning it's a non-signed number. If I'm passing in a negative speed, it's going to convert it to positive. And the reason being is analog write only expects positive values from 0, or non-negative values from 0 to 255. So that's what we're going to do there. So that's fairly simple code. I just wanted to go over it so you would see what the basic code does, but now we're going to get rid of it because that's the basic code. And we're not here to be basic. We want to have a little fun with our coding challenge. So this is the circuit we've done up for the coding challenge. Before I go through the coding challenge code, I'll just mention some things here. So the circuitry here, we've got, this is our geared motor. So again, this DC motor here at the front, I've got a little piece of electrical tape there for a flag. This will spin really fast. This part that with the plastic axles, this gear motor in here, this is like, there's a lot of gear ratio stuff happening on, which is affecting the torque, which is creating a slower but stronger turn, which we would use to obviously turn a wheel or anything like that. So we've got the leads. I'll just kind of quickly go through all the connections, but it's more or less as you would have seen in the circuit schematic, just with other components that we've talked about before. So again, this is where, if you watch the previous videos, I go over button connections and stuff more, which I'm just going to kind of skim over today. So this is the motor driver. We can see that VM pin, which is the voltage for the motor, is connected to the VN pin. Probably can't see it there, but that's the final pin there in the power pins, which is VN, which gets its power from this battery pack, which has 1, 2, 3, 4, 5, 6 1.5 volt batteries for a total of 9 volts. You don't need 9 volts. to power this motor. That just happened to be the battery pack that I had available. You could have powered that less, but important to note that the 9 volts that battery pack does fall in the range of 9 to 15 volts, which is what this microcontroller will accept through the barrel jack. So again, this red wire here connect to VM, and VIN on the microcontroller is what's powering the motor. And then the negative and positive rails of the breadboard are connected through here, through this black and red wire, to the 5 volts and ground on the Arduino. So the power rails are all 5 volts and ground. So you can see, shut this light off a little bit, maybe you can see better. The red wire there, or the red wire, is connected to VCC. So again, that's your 5 volts from the Arduino, because it's connected to the positive rail, which is ultimately connected here to the 5 volts of the Arduino. That's powering the actual motor driver board itself, and then the gray wire there, you can see next to it, is connected to ground. Then the inputs for channel A, we're only using channel A in this video, we just have the one motor. PWM is the first pin there, which is the white wire, and then inputs 1 and 2. 2 is actually the one right next to PWM, and then input 1 are connected through the gray and purple wires. So they're all connected through pins 11, 12, and 13. And we'll see that in the code as well. So that's your input for your motor, connected through these pins. The output, as you can see over here, the output for channel A, that's all we're using, we don't have 2 motors here, is your red and black leads from your motor. And then we've got a voltage divider circuit created here using a photoresistor. So I'm not going to go through this in great detail. I've discussed this a lot in previous videos, but essentially you can look up, it's a voltage divider circuit where I'm using, I believe that this is a 10 kilo ohm resistor. You can look at the color code and see it's got brown, black, and orange, indicating 1 0 and then 3 more zeros. One end of the resistor is connected to ground, and the other end is connected to a common connection with the photoresistor, so both legs are connected in the same breadboard rail, or column rather, and the other end of the photoresistor is connected to power. So this is creating a voltage divider circuit, and the connection is through this orange wire over through this orange wire, ultimately to analog pin A0, one of my analog inputs. But that voltage divider circuit is working so that at a certain point I'm going to be controlling the motor using the photoresistor and the light levels that are read on this photoresistor. I've got my RGB LED here. The common ground pin is connected to ground through this gray pin, and all the positive pins, it's kind of hard to see, I'm going to actually unplug this for a minute so the light goes out. All the positive pins are connected through 330 ohm resistors that ultimately go through these wires here, the red, green, and blue wire. Kind of hard to see here, but this red here, this green here, and this blue wire here, they're all the ones going through that resistor, and they ultimately connect into these 3 PWM pins here, which are pins 6 for the red, 5 for the green, and 3 for the blue. So those are all PWM pins, which I require because I change the intensity of the RGB lights. They're not just on and off like a digital pin, they're values between 0 and 225. So again, these 3 wires are red, green, and blue are connected to the RGB, which has a common ground. I've got a voltage divider circuit set up here for the photoresistor. And then the switch, you can see the switch, the middle terminal is connected through that gray wire to ground, and then that yellow wire connects one of the leads. Again, it wouldn't matter which one, it could have been the other one. It is connected to over here, just for neatness, and then through this yellow wire here. The green wire is for one of the button pins. So again, one of the buttons, this is the motor button. This is going to be the one that controls the motor turning on and off in one of the coding challenges. One end is connected to ground. You can see through that gray wire. And the other end is connected through this blue wire here, which comes to here, and then through this blue wire. And then this green button, which is my menu toggle button, again, one end is connected to ground, and the other end is connected here. So I basically just moved these over here, the switch and the two wires over here, so that they're all neat and together, and then I could use this one harness over here. That's the only reason I brought them over here. They could have just directly went over to the Arduino, correction, in this case the SparkFun Red board, which is an Arduino compatible board. They could have just went over there, but because I had these three little wires that wouldn't reach, and I had this one harness, I just moved them over here and then brought them over in the same colors over to pins 8, 9, and 10. My apologies. So that's the circuit hookup, pretty much there. So again, we're just taking very quickly the ground and 5 volts connected to the breadboard, and both positive and negative rails on both sides of the breadboard are connected together, and that 5 volts is powering the actual motor driver and all the logic, but VIN pin, which is getting its power from the external battery pack, is powering the actual VM pin, which controls the motor, which goes through the outputs for channel A, outputs 0 and 1. The inputs are controlled via pins 11, 12, and 13. And again, we've added some buttons, an RGB LED. The RGB LED, the kite, red, green, and blue, are controlled through PWM pins. And the switch and the 2 buttons are controlled all through these pins. That's pretty much that. Let's plug everything back in. So first, the external battery pack. And we still need to connect the USB cable, because that is going to be used for serial communication via the serial monitor. Let me get back to my... Okay. Some technical difficulties here. There you go. I was wondering where my code was. So now we're going to be going through the code for the coding challenge. So I can do a quick live demo first and then go through the code. Maybe that'll make more sense. And then I'll actually go through the code. So when the code for the program first starts, which is it just did a minute ago when I replugged it in, we get this menu shown on the serial monitor. Motor control changes. Press 1 to go into switch changes direction mode. Press 2 to have the button toggle the motor on and off mode. That's using the blue button. Go to mode 3. Press 3 to go to photoresistor mode, in which case the photoresistor, the voltage divider circuit I have there, controls the motor. And then 4 just changes the motor speed. And the current speed is set at 50. Now you notice the current speed is set at 50, but the motor's not moving. That's by design. When the program first starts, you have to enter a mode in order to get the motor moving. Because I don't want the motor just moving out of nowhere, because then, it's just not safe or whatever. So press the navigation button to switch mode. So you can either enter a command or use the navigation buttons. So if I press 1 into the keyboard, and then I press enter, we're going to see I'm going to turn into switch changes direction mode, which means the motor is going to spin in a certain direction. And I tied this little zap strap on there so you can see. It's going to spin in a certain direction, and when I toggle the switch, it's just going to switch direction. It's not going to stop. The motor is just going to spin forever. So let's press 1. So the motor is now in a forward direction, and now if I flick the switch, the motor just switched to a different direction. If I flick the switch again, it just goes in the other direction. So again, at this point, the switch isn't turning the motor on and off like it did in the original circuit before the coding challenge. Instead, it's just switching the direction. So that's that method. If I press 2, which the menu is no longer up there, but if I press 2, we're going to go into button mode, where 2, you can tell by the RGB LED that's red, where the motor stopped. I have to turn the motor on by pressing and holding down the blue button to turn the motor on. And you can see as I'm holding it down, the RGB is green, indicating that I'm in go mode. But as soon as I let go of the button, we stop again. So, go, RGB is green and the motor is moving. Let go of the button, the RGB LED turns red and the motor stops. I can go into press 3 in the serial monitor. So again, in case you're not seeing here, I'm entering my commands in the serial monitor here. And if I press enter, now I'm in, correction, so now I'm in the RGB LED light mode. Oh no, I'm in the button mode still. And there you go. I'm just changing the mode. There you go. What mode? Sorry, I was trying to remember the mode. So set to 3. So if I'm in 3, I'm in RGB LED control mode, but I think it's too small to be controlled. I'm not sure if I just did something. So right now I'm in mode 3. So the motor shouldn't be off. So in mode 3, oh, you know what? I know what's off. I was going to say, I was confused because when I'm in mode 3, I'm supposed to be in photoresistor mode, where the motor is on all the time unless I cover the photoresistor, in which case it shuts off, the photoresistor. But I realized I shut off the light a second ago. That's why I'm off. So if the photoresistor is all connected properly, it should go. So unless it's got darker in the room, we should be good to go. So I'm going to go to 3, but it still doesn't seem to be working. It was working before the video, so I'll fiddle with that in a second, but let's go to mode 4. Mode 4, we're flashing green and blue. I'll turn the light down again so you can see. It's flashing green and blue, and that indicates I'm in speed change mode, so I can enter a speed. So by default, we started with a speed of 50. If I change it to, let's be 255 and just go crazy, this will be full speed. Now, when I press it, nothing happens. I have to switch out of speed change mode to start the motor again. So I could go to mode 1, where I'm in switch mode, remember? Where the switch controls the direction. I could go to mode 2, where I'm in button mode, where the button controls whether or not the motor is going or not. And normally, mode 3 would cause the RGB LED, the photoresistor to control the motor, but it doesn't seem to be working right now, so we'll figure that out in the code. But that's one way to toggle through the different options. Another way is to use this menu button. So if I press this, I was just in mode 3, which wasn't working, but it's photoresistor mode. And now I'm in mode 4, where I'm in speed change mode. So I'm going to lower the speed to, say, 175. So I click the speed to 175, and now I'm going, that's why I'm stopped flashing, and now I'm going to toggle. Again, this is going to take me from mode 4, the speed change mode, back to mode 1, which is the switch mode, where the direction can be changed by the switch. So when I do that, now I'm in switch change mode, where the switch controls the direction. If I toggle again, I'm in button mode. And you'll notice the switch can do anything in button mode. So I'm flicking the switch. It doesn't do anything. So the switch only works when you're in switch mode. If I toggle again, I'm now in photoresistor mode, but that's not working right now, so it seems like nothing's happening because indicated by the RGB LED, the motor is stopped. But that's probably just a threshold. Maybe the light has changed in the room since I've done this. And then I'm back in motor control mode where I can lower the speed again. Let's go with 100. And I can toggle back through. And now I'm in photoresistor mode again. I'm just going to quickly look to see if I unplugged anything and why that's happening, because it was working just before the video, so I'm just curious if I unplugged something while doing the demo. Okay, there you go. So I obviously had unplugged something. I just fiddled, and now look, when I turn the light on, we're in photoresistor mode, and now the the RGB is green, RGB LED is green, the motor is moving, but if I block the photoresistor, the motor stops. So this is what photoresistor, the light mode was supposed to do from the start. The motor spins at whatever speed it is until I cover it, and then it shuts off. So this is essentially acting as the button before. So if I cover it, so if I keep it covered, it's off. As soon as I uncover, it's off. Or I could shut off the lights and it's off as well, because again, I have a certain threshold set in the code. So that's the different modes. But again, I can toggle via the button. Now I'm in a speed control mode, so I'm going to up that to 100. I can toggle via the button, where I'm in switch mode. I'm in push button mode now. I'm in light control mode. Or, I'm in speed control mode again, where I'll enter 150. So I'm in switch control mode again, or I can control via the serial monitor. So if you'll notice, I'm putting a 2 in the serial monitor and pressing enter. So again, the circuit works, switches between modes via the serial monitor. So again, if I want to go to light control mode, I'll do 3. And now I'm in light control mode. Or I'm going to go back to 2. I can switch via the serial monitor or via the button, the menu button. And I'm just going to put this back in 2, so the motor's off unless we're pressing the button. And now I'm going to go through the code. So that's the demo part of everything. And I'm noticing something I don't like. I have the motor off happening a million times. I've addressed this in previous videos. Instead of having code repeatedly output to the menu, I've used time functionality to only output once. And then, not time functionality, really state functionality, that I output once, and I don't output again unless there's been a change of state. So in this case, if the motor's off, I won't change it again until there's been a change of state. The motor turns on, or I switch modes or something. I obviously neglect to do that for this time, but again, not the end of the world. I might actually add a video later. I'll just update the code, but I won't do it now while I'm doing the walkthrough, because this video is already quite long, as most of my videos are, because I'm not a YouTube person. I'm doing this for the course, but I'm not very good at this video thing. So let's just move this over and we'll go through the code in detail. So as usual, if you followed any of the videos I posted so far, you'll know that I'm a big advocate of Doxygen style comments, which basically are they just allow you to take your code, throw it through an external program like Doxygen, and make really nice professional HTML documentation, so like web pages, detailing your codes and the functions and all that sort of stuff. And it does it automatically for you. And all you have to do is a couple of little things. I've mentioned this previously in a video, so I'm not going to go over too much. But essentially, this little extra asterisk here in what would normally just be a multi-line comment in Arduino allows me to put these tags in, and basically allows me to ultimately put this code through an external program and create some really nice documentation. This just explains what the program does. Again, it's an Arduino program for controlling a motor with different input methods via a switch, a button, and a photoresistor, and RGB LED feedback. The program implements a serial monitor menu and button-based navigation to toggle between 3 motor control modes. Motor control mode 1, where the switch controls the motor direction. The motor's always going, but the switch controls what direction it goes in. Motor control mode number 2, where the button toggles the motor on and off, meaning the motor's only on when the button is depressed. And mode 3, where the photoresistor controls the motor being on or off, where if the light is on, and there's enough light, the motor is on, and then when the light level drops below a certain level, the motor turns off. RGB LED indicates motor speed via RGB color transitions. So I'm transitioning through the rainbow from red, orange, yellow, green, blue, indigo, violet, that sort of thing. I'm the author, and I originally made this code up almost a month ago, but then I got busy, so I'm just getting into the videos now. Not the ideal way to do things, but that's it. So the motor control variables, I'm going to go through this somewhat quick because the video is getting long. If anyone has any questions at all and they felt I didn't go through it in detail enough, or they just need some extra clarification, post your questions in the course forum and I'll try to answer them as quickly as possible and see if I can help you out. But in the meantime, I'm just going to go through at a certain speed So the pin definitions here, I use constants for a lot of my stuff. I just don't like magic numbers, so I'm using constants. So I've got constants for my 1 and 2 for both my inputs for my motor driver, as well as my PWM pin. So again, all these are the pins associated with the motor driver for controlling the motor. Your inputs 1 and 2 control the direction of the motor, and this controls the speed of the motor. And then my motor control pin here, the motor control pin is the blue button. So the blue button is the motor control pin. The green button is the menu pin. I've got some constants representing forward and reverse. Those are just constants for me to use in user-defined functions I've created, so some utility functions. I could just put 1 in the code down there and represent forward and -1 for reverse. I just have these so I can explicitly indicate what I'm doing. It's just a coding style thing. So some helper functions I'm using, or some helper function codes rather. I've got more constants for the switch pin, which is on pin 10. The menu button pin on pin 9, again that's the green pin. The photo pin, which is for my photo resistor, my light sensitive pin. I've got some variables for the max speed, 255, the minimum light, so this is my threshold, which is the threshold I'm using for motor activation. So if the light level goes below 750, that's when the motor shuts off. Menu options, this is just a constant to keep track of how many menu options I have. Right now I have 5. I could change this number at any point and you could add more functionality. And if you're watching this video and using this code to create your own project, feel free to increase this number and add more options, ways to control your motor, maybe via an ultrasonic distance sensor where it only turns on when you get really close or something like that. We've done similar things in previous videos, so feel free to watch those. I think circuit 3C, I do something where a motor turns on if via the distance sensor, the ultrasonic distance sensor, like if you get really close, I shoot you with a Nerf dart. I believe that's circuit 3C, but feel free to look on the videos I post on the forum and see if you can find that. I've got a variable for the motor speed set by 50 at default when I first start. I just talked about how I love using constants, and then I just put a magic number here, 50. I could have created a variable saying, default motor speed 50, but that might be overkill. But you know what? For fun, let's just do that right now, and we'll use a different style. Instead of constant, we'll use define. It's kind of more of a C style programming as opposed to C++. But let's do that, and we could go default motor speed 50. And with the default style, the hashtag define style, you don't have to have an equal sign, so there's no equal sign and there's no semicolon. Just like this. This is just an older way to kind of do constants as opposed to the new C++ way. So I could do that. I could have done that. I've been a little more explicit as to what this 50 is doing. This 50 is simply the speed I want the motor to start off in when I first start the program. So there you go. Default motor speed is 50. One other thing I just noticed is I moved over a comment. Again, this special commenting where I have this extra forward slash, because the normal inline comment just has 2 forward slashes like this, but where I have this extra forward slash and then this less than sign, this is just another style of Doxygen style comments, so that external program, Doxygen program, that uses these tags and stuff, can do some special stuff with this code and output it in a very nice professional way. Back to the main point though here, this mode control variable, it shows the current control mode that I'm in, whether I'm in switch mode, button mode, photoresistor mode, or I'm in the mode to prompt the user for the speed. It's being controlled by this variable. These were original variables I had set up when I had one button. I just had the button state and the last button state. I was using this for debouncing essentially of a button, but then I added a second button. So I have a button to control the motor and to toggle through menus. So this was no longer needed. I could have deleted it, but I just commented it out. This is a Boolean flag that's just used to indicate when the mode has changed. either via user input or button presses. And I'm using that so that I don't output the menu over and over and over. Ironically, I should, as I realized with the constant scrolling of motor off here, I should have done more mode control variables and flags so that, again, I only output something like motor off when the state is changed. And like I said, I might put a video out that updates that, or you could do that yourself. It'd be fairly easy to do. Just kind of the way we use button states to indicate when a state is changed for debouncing logic. You would do a similar thing for to only output something via serial monitor when there's been a state change. All this code here, I know I'm still running along the tooth here. All this, I'll be a little quicker. All this code here we've seen before. It's all for debounce logic. So I've got two unsigned long variables because I've got two different buttons. So I want them both to have their own last time they were changed sort of thing. So this is the menu button one, and this is the motor button. But they're doing the same thing. They're indicating the last time the button was changed, and it's used for debounce logic, along with this constant representing the debounce delay, 50. And same with the state change stuff. So all this is used for debouncing logic. When the menu button state is changed and when the motor button state is changed. They're set to default to high by default because I'm using active low coding, meaning the buttons are held high via pull-up resistor, pulling them up to 5 volts when they're not activated, and when you press them, they go low to 0. All this debounce logic, I've used this in all my previous videos. I'm explaining in more detail. It's basically using non-blocking code, so using this time functionality, so that I don't use delays in my function. I don't like delays. That's blocking. It stops the Arduino program from running. It can cause issues. It's a simple way to do debouncing, but it's not the best way to do debouncing. It's far better to use time functionality and this type of logic. I think I was doing a lot of other things here that I've just commented out. This is code for the RGB LED. Again, just constants for my 3 pins, red, green, and blue pin, and a delay, RGB transition delay. This is just as I transition through the rainbow colors, the Roy G. Biv. This delay just makes it look better. It goes through at a certain speed. These are all my function prototypes. So again, if you don't define and declare your functions ahead of time, like as far as C++ is concerned, if you don't define your function before you use it, you need to use function prototypes, which basically is just the signature of the function declared before you use it. So this tells the compiler, hey, there's a function somewhere in the program called setupMotor. It takes no arguments, and it's a non-value returning function. If you see it before I define it, don't freak out. Just let it happen. So that's what this is. I've talked about this in further detail in previous videos, so I won't go into any more detail. But this is all the functions associated with the motor control. I've got a function setupMotor, just does all the pin modes and sets up your motor. With pin mode function, just keeps things neat. That's the only reason I have it. It's just a helper utility function. Spin motor function spins the motor at whatever speed I pass in. Setup motor direction, again, this just controls the direction you're spinning the motor at. And stop motor, that's obviously just going to call the spin motor function essentially and probably pass in a 0. Button functions, I just have one. Is button pressed? It takes in 3 parameters: the button pin, and I pass in the button state by reference. That's what that ampersand indicates. And the last button changed, the last time the button was changed, which is that unsigned long, again being passed by reference because I need to actually grab those values. I don't want to pass in by value, which is the default in C++ and Arduino programming. I need to pass by reference, these two things. I've talked about passing by reference in detail in further videos, so I won't go into any more. But ultimately, if I call this function is button pressed, it's going to return a Boolean indicating true or false if the button is pressed or not. And then I have functions for the RGB LED. Set up the LED, again, this is just a helper function to keep things neat. So in my setup function, I don't have a bunch of pin mode function calls and stuff. I just have one function that sets up the LED. Typically, it's also convention a lot of times to call your setup functions as like motor init or LED init, like initialize. I've just called them setup, but that's a fairly common practice that you'll find on the internet in a lot of tutorials. I've got a couple functions for set LED color. I've got an overloaded function. So this function has the same name and the same return type you'll see. So set up LED color. One version takes in a single parameter, the speed, which is going to set the color of the RGB LED based on the speed. And then another version is going to take in 3 int values representing the intensity for the red, green, and blue of your RGB LED. So that's just overloading a function. I've talked about that in previous videos, but obviously I had a need to do it in this video. Again, I made this code a month ago. I either had a need at one point. I thought it was better to pass in speed most of the time. I know that's the one I use for the most part, but maybe at one point I thought it'd be better to actually call the just to pass in whatever color I wanted via 3 parameters. Sometimes I might just do this stuff just for the sake of learning. I mean, I'm taking this course to learn, so this could just be for educational purposes that I've overloaded this. I also have a function called flash LED while waiting for input. So that's the one that flashes my RGB LED flash green and blue when I was waiting for the user to type in the motor control speed. That was more or less just a visual cue for me to know, hey, they're still waiting for me to type in a motor control speed. And then I have some serial monitor functions. And again, these are all just the function declarations, not the definitions. This is all under function prototypes. Just me telling the compiler, hey, you're going to see these functions in the code. So if I'm calling them before you see it defined, don't freak out. So again, I've just got functions here for serial monitor functions, change mode, check for user input, and print menu. They're pretty self-explanatory what they do. As well as the helper functions for the menu selection options. Remember, there's 4 different menu selection options. Toggle direction with switch, that was one of the options. Button mode, where I have to depress the button to turn the motor on, another option. Photo mode, where the photo resistor controls whether the motor's on or not based on the light level. And another mode where I was prompting the user to enter the speed. So these functions just literally take care of the menu options. So in the setup function, I've got, I call my setup motor and setup LED function. Again, in those functions, there would be all the pin modes for the motor pin and LED pin, but it's all taken care of just by calling these 2 functions. That's the only reason I made them, just to keep things neat. I chose not to make one for the buttons. I could have made a, hey, set up buttons. I didn't, because again, I'm showing different options of doing things, because this is an educational video, an educational course. But I call the pin mode function for all of the buttons, the switch pin, not a button, but a pin, switch pin, the menu button, and the motor button pin. And I'm calling input pull-up for all of them. So that means I'm using the internal 20 kilo ohm resistor with each of these pins, as opposed to an external resistor where I could just include a physical resistor in the hardware. Sometimes it's just easier to do this. However, the advantage of using an actual physical resistor is you can control the resistance level. When you call input pull-up, you're just using the internal pull-up resistor with that pin, and they're all 20 kilo ohm resistors, I believe. So there's no option to choose the resistance level. But for my purposes, that's quite fine, and it saves me some components. And the more components you add to a circuit, the more chances wires get moved, or the more chances there are for failure. So hey, when you have the option to use the software, i.e. the Arduino IDE, and just call input pull-up, use it. I'm also starting the communication with the serial monitor at 9600 baud rate, and then I'm calling the print menu function, which was that menu that when you first start the program, I'm just going to reset the Arduino here. When you first call the program, it prints off this menu. That's what the print menu does. So I'll just reset that again. And then the loop, as usual, it's the Arduino main loop function, and it simply continuously checks and handles the selection mode. So depending on which of these modes I choose, am I going to do switch changes direction, button toggle motor, photo resistor, change motor speed mode? Well, the loop is going to determine what I'm doing there. So first thing I do is I call these 2 functions, use button to toggle menu, I call that function, and check for user input. So basically, these are the 2 ways that I toggle the menus. I either use that button, that green button, that I was using to toggle the menu, right here, or I check the user input. Remember, I can toggle by just typing in something here, like a 1, a 2, a 3, or 4, whatever. And then I'm using the switch statement, which just takes in, an integer type value, and or an integral value really. It can be character, anything that kind of evaluates to an integer behind the scenes. And depending on what gets passed in here, I'm going to just either print the menu, which is this menu here, which is how we start off in default at 0, because you'll notice that my mode is, where am I? My mode is 0 by default. I start off in mode 0, which is why I print the menu when I first start the Arduino, because I go to case 0, print menu, and then break. If I enter a 1, I'm going to just break this up here. If I enter a 1, I'm going to call the toggle direction with switch function, because again, 1, switch direction, change. Case 2, I'm going to go into button mode, because again, option 2 was button toggles motor. Case 3, I'm going to photo mode for photoresistor, because case 3, photoresistor controls motor. And case 4, prompt user for speed, because 4 is change motor speed. And I'm opening the current speed is 50 because I just started the program, and 50 was the default speed. And then default I just break, because there's really no default. You just go back and do one of these things. There's really no way to get to a default, because I do validation checking when the user is typing something in. So then the motor functions, I understand I'm still being quite long with the video, so I'll try to get a little quicker here. Motor functions, setup motor simply calls the pin mode. It sets up all the pins as outputs and does the digital write low for both inputs 1 and 2 at the start. That's one way of just turning the motor off. And then I'm analog writing to the PWM pin the motor speed, which is 50, but it doesn't matter because when both inputs are low, that's telling the motor not to move. Alternatively, I could have not had these two lines of code and just started off the motor in 0. But because I'm only calling the setup motor function once in setup anyway, and I know I want to start off 0, so I could have just avoided these two lines of code and had 0 put in here instead of motor speed, which we know is default to 50. But again, there's lots of different ways to accomplish the same thing in programming. That's one of the beautiful things about programming that I love, is there's just so many different ways to accomplish your task. It's just based on what you do. So just one way to do it. And then I just output, hey, motor setup complete, motor stopped. In the spin motor function, I'm taking in a parameter of type int rather, speed. And again, based on the Doxygen style comment you can read here, it says the motor speed is between -255 and 255. If the speed is positive, so if it's greater than 0, I'm going to call a helper function, set motor direction forward. Else, if the speed is meaning if it's not positive, it's going to be negative. Actually, technically, I'm realizing something here. If it's not greater than 0, it could be 0 or negative, and in either case, I'm going to call the set motor direction function, passing in reverse, which is not technically accurate if I passed in a 0, but it doesn't affect the actual code, and you'll see why when I go to the function. But it might be better to actually have said else if. In fact, I'm going to change it because it would be better. It'd be better to go else if set motor direction. Else if, let me just change this right quick. I understand the video is already long, but this just makes it a little better. Else if the speed is less than 0, then I'm going to set the motor direction to reverse, and I'm saying speed equals negative speed, so I'm taking negative speed and assigning that to speed, just to convert to positive for PWM, because you can't output a negative to when you're doing an analog write to PWM. It has to be a positive value. So this is essentially my way of just making an absolute speed. I'm taking what was a negative speed, because obviously I only came into this if statement because the parameter that got passed in was negative. So I'm taking that negative value, this would be a negative value, and I'm negating it by putting a negative sign in there. And as we know, a negative and a negative make a positive. Negative times a negative make a positive, which will mean the speed will be positive. Because I'm going to take care of the direction inside this set motor direction function. But I need the speed just to be a positive speed. So that's all this is doing. I could have accomplished this exact same thing by just taking the speed and calling the absolute function on speed and passing in speed, and that would have taken a negative speed and made it positive. So that's that. But now that I've done this, where I've said else if speed is less than 0, I have to include another else. And I would simply go else, and I know this else The only other possibility, if I'm not a positive speed and not a negative speed, I can only be a speed of 0, and I could just call this function here analog right to 0. I would have to put in a 0 here, and that would be but then it's going to get called again here anyway with a 0. So I actually really don't need this else statement. I guess I was trying to change the code. So the way I have this set up, there's really no need to put an else because I'm not going to do anything else. I'm not going to call the set motor direction speed. So in this case, I probably will change it back. I understand this video just got really weird because I'm going to go else. I would, if I really wanted to change the logic of this, I could change the way the coding, but right now, without making a bunch of live changes, which when you're changing code live like this, little tweaks might affect the whole code. I won't do it. But I understand that in this particular case, this is kind of off because it says, hey, if it's a positive speed, set the motor forward, else set the motor in reverse. But we really wouldn't be setting the motor in reverse if it's a 0 that got passed in, but it just isn't going to matter. It's still going to stop the motor, so you're still going to get all the same things. It just doesn't make as much sense this way. I could change this, but again, it doesn't really make sense. Either way, you're going to set the motor forward or reverse. Understand if a 0 got passed in here, we would have came in here in the reverse, but we're not going to move anyway, so it doesn't matter. And then after we jump out of that, that's setting the direction. This is all just setting the direction. Then I'm going to set the speed, the motor speed, using an analog right to my PWM pin. Remember, the analog right only works on PWM pins, which this pin is for my motor. And then I'm passing in the speed that got passed in. So this controls the speed. This controls the direction. So depending if this got passed in positive, we'd be going forward. If it got passed in negative, we're going to reverse. And remember, these are the constants I had up at the start of the program. This is my constant forward equals 1, and this is negative 1. And then I'm setting the color of the LED based on the speed and this set color function. So set motor direction, again, this function, you can read the document comment, but basically I pass in a direction, 1 or negative 1, which is being passed in by my constant values that I've created, forward or reverse. 0 for stop, again, I guess I intended me to pass in a 0 for stop, but I never end up passing in a 0. So in this case, when I pass in if direction equals forward, meaning I pass in the constant forward, then I'm going to set analog. So channel A input 1 to high and input 2 to low. That makes me go forward. If it was reverse, I'm going to put low for input 1 and high for input 2. And again, this is all in the documentation for the motor driver. Else, I'm going to stop. I'm going to put them both low, and that's going to stop. Now, based on what we just seen, we know this is never going to happen else because a 0 is never going to come in here. I'm only calling this method by passing in a forward or reverse. I'm never going here, but it doesn't matter because even though if I change the direction to reverse, which I technically will up here, if I pass in a 0, I am going to change the direction to reverse, but it doesn't matter. The direction's technically going to be reverse, but then when I call analog right, the motor's not going to move. And then the next time I change, next time I call anything, I'm just going to move anyway. So it doesn't actually affect anything in the code. It's a little icky, I guess. And I'll fix that when I go to upload it probably. If you have any questions, if I've confused you in the last 5 minutes or in the last hour and some, let me know. Stop motor simply writes 0 speed to the PWM pin using analog right, and it sets the color to red. So remember, I have an overloaded function here, set LED color. I can either pass in the speed, with just one integer representing the speed, or I can pass in 3 values representing the red, green, and blue intensity. And when the motor stopped, I just went full red, 255 for R, and green and blue, I just leave it 0. So you notice I'm using both types of set color. Here, I call the set color LED function I created, passing in just the speed, 1 parameter. Here, I'm passing in all 3 parameters. Button functions here, you can read this document style comment I've created that basically just tells you what's happening. I'm using time functionality for debouncing. I have these parameters, but that's all saying basically what I'm doing. I gotta make this video a little quicker. I'm using same time functionality and non-blocking code I've used in a lot of other programs. to get my debounce. I get the time using the millis function as soon as you come in the program. And then I say, hey, if the time now minus the last time the button was pressed, if this duration is greater than the debounce delay, which I have set at 50 milliseconds, then I'm going to do a digital read of the button pin. And whatever that is, I'm going to assign that to new button state. And if that button state is different than the previous button state, so if there's been a change, well, then I'm going to update both the last time the button was changed to time now and the button state to the new button state. So that way they're updated for next time I press a button. And then I'm just going to return true or false depending if the button state equals low, meaning it is being pressed. If that's true, I return true. I also return false. And if I never came in here in the first place, is button pressed? Well, if I didn't come in here anyway, meaning I'm either not past the debounce delay, or I didn't press the button, I'm returning false. I normally would go through this in more detail, but again, I'm running really long here on time. But I've went through all the button debounce code in previous videos, so just look those up if you have any questions, or post them on the forum and I'll answer. RGB code. This code, again, I'll try to go quickly through, but really, to go through it in full detail, you might want to pause it and look over it, just because I don't want this video to get longer than it is. But setup LED, I basically set up all my red, green, and blue pins as outputs, and then I use, this only happens when the LED first sets up the program. I iterate through all the colors of the rainbow, going from Roy G. Biv, from red, orange, yellow, green, blue, indigo, and violet. And indigo, if you're not familiar with that, that's like cyan in computer speak, and violet is magenta in computer speak. But I use a bunch of for loops, and the for loops, all they ever do is they're changing the intensity of one color. So again, and then I'm using inside the for loops, I'm doing analog writes and a delay to output different intensities to the red, green, and blue LEDs associated with the RGB LED, and then I have a small delay that's just for aesthetic purposes so that it just doesn't go that quick. So I believe I have it set up at 3 milliseconds. Yeah, 3 milliseconds. And every for loop just changes one color at a time in order to change the intensity. So I'm going from red to orange in this case. So I have full red at the start, no blue, and I'm increasing green. It starts off at 0, but it increases up until it's 127, about halfway, because again, there's 256 different values that you can output to your analog pins via analog write, 0 to 255. So 256 divided by 2 is 128. So from 0 to 127 represents halfway. So basically, I start off at full red and I increase up to halfway through green, which gives me an orange color. And then I continue increasing. I just separated this because I think I was doing different things. This could have really just been one code. As I'm looking at this, this all could have been one for loop, and instead of having this go up to 127, I just go up to 255. There was no need for both of these. As you can see, nothing else changed. This code is all the same in both for loops, and I've only changed, I'm basically going like this. I'm having a for loop, changing green from 0 to 127, and then I start at 128, the next bump after 127, and then go to 255. There was no reason to have two for loops here. I'm just realizing this. I originally was changing how I was transitioning colors. It wasn't necessarily Roy G. Biv. I was going between just blue and magenta and stuff. I obviously settled on Roy G. Biv and didn't realize this is completely unnecessary. So this could all be one for loop. In fact, I suggest if you end up doing this code on your own, change this to one for loop where you just green is less than or equal to 255. And that would be that'd be better. But ultimately, this takes you from red to orange. This for loop does, and this takes you from orange to yellow. If we made it one for loop, it would go from red to yellow. I think maybe that's why I did it. Now that I think about it, I wanted to be explicit about the Roy G. Biv. This is going from red to orange, orange to yellow. I think that is actually why I did it, so I could separate the Roy G. Biv thing. Okay, and then I'm going yellow to green. Yeah, Roy G. Biv. So to go to yellow to green, I'm just decreasing the red. So I just leave green at max, still not touching blue. Blue is still off. Same delay throughout the whole thing. But I'm decreasing red from 255 all the way down to 0. And that'll take me from yellow. Because remember, when I have full, this takes me ultimately from red to yellow by the time I'm done the second for loop. Where at the end of the second for loop, I have full red and full green. And if you remember, red and green make yellow. So then when I start decreasing the red and just keeping the green, I get down to full green, because by the time this gets down to 0, no red, I just have full green, and that's what color I'm at, yellow to green. And then to go to to go to green to indigo or cyan, indigo in kind of the Roy G. Biv, it's I for indigo, but cyan is how a lot of computer people know that same color. They're essentially the same. In order to do that, I just need to increase blue, my color blue. So I increase from 0 intensity to full intensity at 255, keeping green at max the whole time. So I'm going from green to cyan, because again, when this gets to 255, I'm going to have full green and full blue, and that is what creates cyan. It's equal parts green and blue. It's that beautiful aqua color you know we all think about when we think of the ocean and Hawaii maybe. And then go from indigo or cyan to full blue, we have to get rid of the green. So we just decrease the green from 255 down to 0. And then we're full blue. And then we go blue to violet, which is magenta in computer speak, just a purple for guy speak. We do that by increasing the red. So we've got 0 green at this point, full blue, 0 green, full blue, and we're just going to increase the red from 0 to 127 again, halfway intensity. And that'll take us to violet. And then now again, I could have got full purple too by just going to full intensity red. I stop halfway, and the reason being is because then I'm wrapping around back to red. I'm just going to wrap around to full red by going violet to red by decreasing the blue. But again, I'm noticing another mistake I made. But you know, that's what these videos are for, to show, hey, I'm seeing mistakes. I only increased to 127 here, which is half intensity, so it's going to be a nice color magenta. It's going to be a nice color, but it's not full purple. Full purple would be full intensity red, full intensity blue. Whereas this, I'm having half intensity red and blue. So I'm going to still have slightly more blue tinge than red, making it not like ideal purple, but you know, it'll be a nice color. But then immediately in this for loop, I just switch. Red starts off at 255, and I start decreasing blue down to 0 to get back to red. So this is my wraparound, Roy G. Biv, and now I'm at the end of this for loop, I'll be back to red. But again, this should have probably been 255 because I stop at 127, but then it's immediately 255 in this code. So I'm just going to change that. Again, I probably should have changed these two for loops to be 1. I just had them separated for the explicit nature of going red to orange, orange to yellow, just to help me with the Roy G. Biv thing. That was meant to be quick, and it wasn't at all, but that's basically only happens once at the start of the program. I set up all my pins as output, and I iterate through the colors of the rainbow. I guess I just like colors. It doesn't happen ever again. After that, I have my 2 functions, both named the same name. They're overloaded functions. Set LED color. One takes a single parameter, the speed, and it sets the color of the RGB based on the speed. The next one takes in 3 colors and kind of more of a traditional set color function, and just sets calls the analog rate, passing in the 3 parameters, red, green, and blue, and setting the RGB at the intensities of the 3 parameters passed in. Now, so that one's as usual. I'm not going to go over that one. Setting based on the one color, I take in the speed. I call the absolute function on it right away, which changes it to, if it was a negative speed that came in here, I'm just making it positive. Because again, when you're outputting to a PWM pin, it only accepts values between 0 and 255. It doesn't accept negative values. So this absolute function is accomplishing the same thing that I accomplished up here in my speed function, where I went like this. If I had a negative speed, I timesed it by negative, like, you know, timesing anything by -1. If you have a negative times a negative, it becomes positive. This is essentially doing the same thing. I'm just doing it now with a built-in function called the absolute function, which returns an unsigned version of the speed. And then I use that unsigned version of the speed, and I use the mapping function to map whatever that speed is, which we know is going to be a value between 0 and max speed, which is 255, and I'm going to map that from 255 to 0. So if my speed that I got passed in is 0, I want 255 for red intensity. I want full red. Why? Well, because if max speed is 0, that means I'm stopped, and I want a red light when I'm stopped. And if it's max speed that got passed in, meaning I'm going at a good clip, 255, well, I want 0 red, because I don't want any red in the RGB LED. You're green. So the opposite is true for green. I'm mapping the absolute speed that's still from 0 to max speed, But if I'm 0, I want 0 green. Because if I'm stopped, I don't want any green. I want you to be red. If I'm max speed, I want 255. Because that means you're at max speed, I want full intensity for green. So again, and I'm not doing anything with blue, just for simplicity. I'm using traffic lights, red for stop, green for go, and everything in between. You're going to transition from green to red depending on your speed in between these two extremes. And I'm just calling the analog right 3 times on these values. And then finally, I have this function flash while waiting for input. This just flashes between, again, I'm calling my set LED color function this version that takes in 3 parameters, just by passing in the colors here. I think this is why I created the second parameter, just so I could do this. I could flash between blue and green, because again, RGB, so this is the B, blue, and this is the G, green. I'm just flashing between green and blue with this delay, whatever the delay time is that I passed into this function. And that's just a visual indicator for me to know that I'm on the mode of, hey, enter speed. I've got a lot of serial monitor functions here. Check user input. Again, I'm really running long for time here, so I'm not going to go over this. You can pause the video, read the Doxygen style comments here. But basically, I'll just read this Doxygen style comments and you can go through the code in more detail yourself. But basically, I'm just pulling the serial monitor for user input to toggle between the menu modes or select a specific menu option. If the user types the spacebar, the menu mode toggles to the next option. I forgot to show that in the demo. If the user types a number from 1 to menu options, in this case, whatever the menu option constant is, it sets the mode to the selected option, and invalid inputs are ignored. So again, when we come to this function, it takes no parameters, it doesn't return anything, it just, as the function says, checks for user input. If you're going to check if data is available from the serial monitor, so basically if serial.available is greater than 0, I'm going to use the serial read function. This is not parseInt. I'm actually reading in a single character from the serial input and assigning it to user input. This is different than parseInt, which would actually grab an input directly. I'm using kind of a different technique to do it. A little more convoluted actually, if I'm being honest, but I'm doing it for educational purposes. This is going to read in a character, and then I'm going to check that character. If that character is a spacebar, I'm going to toggle to the next menu option. So I'm going to go mode equals mode plus 1 mod menu options. And this functionality, I've used this in previous codes, and I explained it in more detail there, but it essentially allows the mode only to wrap around and toggle between 0 and whatever my max option is. And then it loops back. That's what the modulus operator is doing for me. I explain this in more detail in other code. Feel free to look that up or ask any questions in the forum. And then I'm changing, this is a Boolean flag that I'm using to decide whether or not to show the menu. This just basically means I don't show the menu over and over on the serial monitor. And this is the code I kind of mentioned. I need more of these flags so that I'm not always outputting, well, it's not happening right now, but if I go to button mode, where I'm always outputting motor off, I shouldn't be outputting that over and over. I should have output it once and then not done it again. I need more of these Boolean flags and changes of state functionality to do that, and I'll do that in another video. This is just verifying that they only input valid data. If the user input is greater than or equal to the character 1, not the number 1, the character 1, not the integer, and the user input is less than or equal to the character 0 plus the menu options, this will just end up being the character 5 or 4 or whatever menu options I have, 5. If that's true, if it's valid input, basically, hey, if it's valid input, then mode equals the user input minus the character 0. Again, this is just the way to convert a character to an integer. User input is a character minus the character 0. It gives me an integer value, basically, that represents the actual value that I typed in the character. This code, in combination with this, is just accomplishing the same thing as parseInt function. It's just more convoluted. And it's really just for educational purposes that I've done it. This is just a function to clear anything still in the buffer. This is a print menu. It just outputs the menu to the screen. You know, when you first start the program, it just outputs that menu to the screen. And that menu there. That's all that's doing. Menu change functions. Each of these functions just handles one of the different menu options. When I'm in the use button to toggle option, so this is controlling, this is when I use that green button to toggle between the menu. That's being done with this. If is button pressed, that function I created, that takes the menu button in, the menu button state, the last time button changed. Hey, if this returns true, meaning the menu button was pressed, and this takes care of all of the debounce logic and everything, then I'm going to change the mode. If you've pressed the green menu button, I'm going to call the change mode function, which is right here. And it just cycles through the modes and displays the selected mode in the serial monitor. So, and it uses the same coding I used before. Mode equals mode plus 1 mod menu options, which this just allows me to cycle through 1, 2, 3, and 4. And I think before I did alternative, I could have done mode equals mode plus 1 mod. Oh, sorry. I had this comment because originally I was doing it the way I did it up there. Don't worry about that. And then mode equals trained, I set the Boolean flag to true. So this code here, these two lines of code, are doing the same thing that's happening right here. The same thing. So whether I'm changing mode by pressing the spacebar, which is what this is checking for, or I'm pressing the button, the menu button, and then calling the change mode function, the same thing's happening. And then I'm saying mode change to whatever the mode is. Toggle direction with switch. If you've selected that option, I'm basically checking if the switch equals low because it's active low switch. It's pulled high by that internal pull-up resistor if it's not being switched. And then if it's low, I'm calling the set motor direction forward. I'm switching and calling the spin motor function at whatever motor speed the current motor speed is. This is a global variable. And then I'm just outputting to the serial monitor that we're going forward. And I output that over and over and over again because I didn't incorporate the right coding so that it wouldn't continually scroll. Else, meaning if it's not low, well then it's high. And then I'm just going to go in the opposite direction. Motor direction, motor speed direction, I'm passing in reverse. And I'm passing in, the motor speed is whatever the motor speed is set already. I need to add a negative in front of it so that it becomes negative motor speed and then call the spin motor function on it. And then I just output that to the serial monitor. Button mode. If I'm in button mode, basically I have to be depressing the button. Remember, these are active low buttons. So if the digital read of the button pin, meaning that blue button, the motor pin, if that's low, then I'm going to call the spin motor function with motor speed, and I'm going to say, hey, motor on. Else, motor's going to be off. I originally just didn't have a stop motor function. I just had the spin motor function. I just passed in 0 to it. And then I end up just creating a stop motor function, which really just calls the spin motor function passing 0. So it wasn't really necessary. I just did it so that this is more explicit to me. Hey, what's happening? Oh, I'm stopping the motor. So that's why I did that. Photo mode basically just does an analog read of the photo pin and assigns that to a local variable light level. And then if that light level is greater than the min light level, which is a global constant, I've set it 750. If it's greater than that, then the motor is going to be on. So we're going to call the spin motor function, passing in motor speed, whatever the current motor speed is, and output that to the serial monitor, indicating that we're on. Else, I'm going to call the spin motor function passing in 0. So here I call the spin motor function passing in 0, and here I call the stop motor. Again, I often do different things to accomplish the same thing just to show the educational purposes. There's so many different ways to accomplish the same thing in programming. That's the beauty of programming. Prompt user for speed. This function, as it says, it just prompts the user to enter a speed between -255 and 55. I've got a couple local variables to keep track of the speed and whether a Boolean flag to indicate whether their input is valid or not. While they're not giving me valid input, so while not valid input, I'm just going to keep asking the user to input a proper thing. So if I kept inputting just various weird things, I would just keep looping forever by saying, just making them redo it. Once they put in a valid input, meaning they read the comments and they know they have to put in something between -255 and 55, then I'm going to come in and go, while not serial.available, I'm going to wait for the user to input a motor speed. And while I'm waiting, I'm calling my flash LED while waiting for input function with a delay of 100. So I'm just, every 1/10 of a second, I'm switching between blue and green on my RGB LED. That's just a visual cue for me knowing that I'm in the prompt user for speed thing. And then if there is something available to read, if the user has typed in something in, I'm using the parse int function to get my speed. So again, before I was using the serial.read function, I was doing this whole convoluted thing. Let me just go back up there to show, just so you can see the difference. So I was using serial.read to read a single character from serial input, assign it to a character variable, and then I had to take that character variable minus the character 0 in order to convert it into a string, something that mode understood as an integer, rather, not a string, as an integer. And all that confusion and convoluted code is all taken away by just calling serial.parseInt function. This just returns an integer. Your input is an integer right away into speed. And then if that speed, which is now an integer, so I can check it using integer values, not character values. If the speed is greater than or equal to -255 and Boolean and less than or equal to 255, meaning if it's a valid speed, then I'm going to set my Boolean flag to true. Valid input equals true. Mode equals 0, because I just want mode 0, nothing to happen. Mode 0 is where the menu is output. And then mode change is true. That's what I'm going to do. Else, I'm going to say invalid input, please enter a different number. A number between this and this. And then while there is stuff available to read, I'm just going to clear any remaining stuff. Like if they typed a value, basically if I typed in something like 255 and then a bunch of other junk, I don't want that screwing up my code after, so I'm just going to clear it. And then I just say the motor's set to it. So that was a very thorough walkthrough. I apologize, the video is over an hour and a half. That being said, I'm still going to do a quick demo, but hey, we've already done a demo, so now's your point to escape. You don't have to follow this demo. I mean, obviously you didn't have to stay for any of it anyway, but you can definitely leave at this point, and there's nothing new going to be gone over. I'm just going to show the code happening again, just because now we've walked through. So, just do this. We're going to restart. And welcome back. If you're still watching the video, that means you're expecting a live demo of the circuit again. And through the magic of YouTube, you are going to get that, but it's actually hours and hours later because it's Friday night and the holidays. So I did have to take some time out to spend with family. But I just wanted to mention a few things before I get right into the live demo. I did adjust some of the code. So before, when I was showing you guys the circuit, we had the code would just scroll and scroll here in the serial monitor, and it was very hard to parse any actual data from it. So it would just scroll over and over, motor on or motor off, or when I switched the direction from motor forward, motor direction reverse. It was just really hard to actually, discern any information. So I did adjust that using some state functions. Basically, I created some Boolean variables to keep track of the state of the motor and the direction. As well as I created an enumeration that would allow me to output things to the serial monitor only once, like when I toggle between different code challenge modes. I only want to output the code challenge mode that I'm in, like a message once, and then not do it again. So that's some of the things I changed. I did run into some issues too that I'll discuss at the end of this video. I'm going to try to keep it short, just show the coding challenge. Just show the live demonstration, and we'll talk briefly about the code that I have changed, just because I did some interesting things with ternary operators in order to accomplish some stuff. So we'll do that, but again, this is all extra, so at this point you've learned everything that you're going to learn for Circuit 5A, the coding challenge. I'm just kind of showing you some extra stuff. So again, if I restart the circuit here, whenever I restart the circuit, the RGB goes through that transition through all the colors, Roy G. Biv, ending at red, and then the serial monitor prints out here. So as before, we have different ways that we can toggle through the different menu options. I can actually just type in the serial monitor the numbers associated with the different menu options, like one where I can be in the switch changes direction mode, where this switch will change the direction whether the motor is spinning forward or in reverse. I can go in button toggles mode, where the button toggles the motor, meaning depressing the blue button will turn the motor on, and not pressing it will turn it off. You'll notice when the motor is off, like it is right now, the RGB LED is red. It'll be green, some varying degree of green when the motor is spinning based on the speed. If I enter 3 into the serial monitor, I'll go into photoresistor control mode, in which case the motor will be spinning at whatever speed the motor is set on, and will only stop spinning when I cover the photoresistor here, and the light level drops below some threshold that I've set. I can also press 4 and then therefore change the motor speed. Right now the current motor speed is 50, but the motor is off by default when you first start the program. But that'll allow me to change that. So I can always have typed things into the serial monitor, and I showed you that before, to toggle between the different menu options. You know, select a menu option and go right there. I didn't show this before, but we could also type the spacebar. I could just enter the spacebar and I would just toggle between the menu options. You know, going from 1 to 2 to 3 to 4, that sort of thing, and wrapping around. It essentially has the same effect as the green menu button. So again, as before, I could toggle through the different menu options pressing the green menu button. Right now I'm in the switch control mode, and you can see that by the motor turned on, motor forward, and the switch control mode. The switch coding challenge mode. You'll notice I'm not printing motor on or forward on over and over. There was some extra stuff that did get printed here. That's some debug code I forgot to comment out. It's no longer needed. But, so this stuff, these 4 lines aren't actually needed. This is the non-debug code. But yeah, so I'm in switch control mode. If you remember, this allows the switch to change the direction that the motor goes in. And you'll notice over here, it says motor reverse, but it only printed out once. It didn't keep printing it out. Just like now, motor forward, it printed out again, motor reverse, motor forward. But again, it's not constantly printing to the screen. It only prints when there's a state change. I could press, again, I could toggle via the button. I'm now in button control mode, where again the motor's off, indicated by the red RGB LED, and it'll be on when I press the button, in which case the RGB LED turns green. So again, when it's off, when the motor's off, the RGB LED is red. When it's on, it's green. I could toggle again. Now I'm in the photoresistor mode, where the RGB LED is green, indicating the motor's on. Now it's off. On, off. And when it's off, the LED is red. And again, you'll notice in the serial monitor, I'm only printing it when there's a state change. I went into the photoresistor challenge mode. I shut the motor off. I turn it on. I shut it off. I turn it on. I'll just clear this. I could, again, toggle into the speed control mode, where I can enter a speed to change the speed. The LED flashes blue and green. I'm going to enter a speed like 150. Again, the change isn't immediate. Now we're just showing the display menu again, but you can see that the speed has changed. So again, change motor speed. The current speed is 150. It just hasn't taken effect until I toggle over, and now I'm in the switch control mode again. I can also toggle via the serial monitor if I type in 2 into the serial monitor and press enter. So you might not have noticed that, but I typed in 2 into the serial monitor over here, pressed enter, and I entered the button challenge mode. Again, this was the big thing I changed for this code, so that I'm only printing information in the serial monitor when there's a state change. I'll just clear that. So again, I could toggle pressing 3, and then I toggle into photoresistor challenge mode, where I can stop the motor via changing the light level. Clear that up. Switch into press 4, and now I'm in, you can see by the flashing, I'm in the motor control mode again, so I'm going to go 75, and then, I can toggle back to switch control mode if I want. I can also toggle via the spacebar. If you'll notice over here in the serial monitor, I'm not going to type a number, I'm just going to press a space and press enter. So the spacebar toggles, now I'm in button control mode. It toggles the same way that the green button toggles. Because now, look, I'm in photoresistor mode. Where again, the photoresistor mode. Again, now I'll press the spacebar again, and now I'm in enter speed mode. I did toggle into switch control mode. I just decided not to stay there and actually do any switch control, just because it's incredibly loud on this table and it is really late at night. So I immediately I pressed the spacebar again to enter button challenge mode. But anyway, that's enough of the live demo. I just want to show you basically that I made a change so that way I wasn't just constantly printing and scrolling information to the serial monitor. Instead, we're only outputting when there's a state change. And I just wanted to show you that we could toggle via the spacebar. In addition to, the green menu button. So yeah, that's all I wanted to show you for that. I'll just give you a quick coding demo, or walk through any coding changes. There's not many changes. The basic changes are all here. This is really all the changes associated with only outputting to the display. All this code is associated with only outputting information to the serial monitor when there's a change of state, i.e. when the motor changes state. So I have a motor state, a last motor state. You guys can pause the video and look through this on your own. It's with the comments, it should be fairly clear what's happening. If there's a change in direction, I also want to output to the serial monitor when I'm going forward versus reverse. I use an enumeration type, an enum type, to allow me to only output to the serial monitor when I've actually switched menu options. And I'm not going to go through enum type right now because, again, this is meant to be a quick video. But basically, these are integers under the hood. So they're like constant values that really are integers under the hood. Menu mode is the value 0. Switch is the value 1. Button is 2. Photoresistor is 3. And enter speed mode is 4. Again, these are variables to track the current mode and flags for displaying messages. So I have a bunch of Boolean flags, and because I have a few of them, because I have a few different menu options, I'm using a one-dimensional array of size menu options, one-dimensional array of Boolean values. I'm setting them all to false at the start, because at the start, nothing has been displayed yet, so I want to be able to display everything once the first time. And this is just the current mode that we started. There's no real changes to setup. The function prototypes are, although I should have added one, but I think I did, or if I didn't, it's working anyway. Setup, the only change I made was I added this function, display mode message, which takes in a mode, the current mode being 0, and displays an appropriate message accordingly. We'll see this function in a minute. I also included this function in the loop, so it displays in setup, and then it displays every loop, again, based on the current mode. There's no change to the setup motor function. So there is a change to the spin motor function. So I commented out the last spin motor function, because you may remember me, I mentioned that if the speed was positive, greater than 0, I set the motor direction to forward. Whereas if the speed else, I set it in reverse, and else incorporated 0. Because remember, if the speed is greater than 0, well, that means positive, non-zero values. Else included 0 values and negative values. And so, although this didn't actually affect the code in any way, the code worked the same. Semantically, it was weird that 0 meant that I switched to reverse. Really, 0 should just mean stop. Again, it didn't actually affect the code because of the speed is controlled down here with this analog write, where I write to the PWM pin, whatever the speed got passed in, and if the speed's 0, the motor's off, so it doesn't matter. And obviously it didn't affect the color of the LED either. Again, speed got passed into the set LED color, and a speed of 0 just would have set the color to red. So there was no change fundamentally. There was no actual practical change that was required for the spin motor function, but I did take the opportunity, well, I was revamping the code anyway, to change it so that it made more sense semantically, like there was a forward, a reverse, and a stop, depending if the speed was 0. I also took the opportunity when I did change the spin motor function, so this is a new upgraded function, use some ternary operators and just some, somewhat convoluted code Not as clear as it would be if I used a bunch of if-else statements, like an if-else ladder, but I wanted to do it. This is an educational video. This is, I'm on COM 444 to learn and try different things. So this is more convoluted and not necessarily best coding practice in one sense. It's more concise, one line of code. So some people like that, but it's not clear. It's not as clear as it would just be using if-else statements, in my opinion. But I wanted to show you guys. So as before, the spin motor function takes in a parameter of type int for speed. And then if the speed is not equal to 0, meaning the motor is on, if the speed is non-zero, then I set motor state to true. Because again, it evaluates this expression, speed not equal to 0. Well, if that's true, motor state is true. If speed is equal to 0, well, motor state will be false. So again, that's the whole purpose of this is so that I'm only outputting to the serial monitor if there's a state change. This is where some of the complication comes in. I'm setting the direction, which is an int variable, based on this ternary operator. And a ternary operator is this thing where you have two operators, the question mark and the colon here, and three operands, meaning an expression that evaluates true or false, one of the operands that gets returned if this expression evaluates to true, and the other operator that gets returned if the expression evaluates to false. So here's how it works. This expression, speed is greater than 0, so if speed is positive, non-zero, then if that's true, I'm going to do whatever comes after the question mark. So I'm going to assign forward to the direction, local variable. Else, if it's false, if this evaluates to false, I'm going to do what follows the colon, which is this. But it's a little tricky in this case, because instead of just returning reverse, which is kind of what I would have done if I was following the last logic, it would be easy. It would just be reverse here, and that would be, we'd be done. But in this case, I have a nested ternary operator, so I'm doing another ternary operation if the number is 0 or negative, so it's non-positive. So it's kind of like a nested if statement, because again, you can consider the ternary operator as a very concise if-else statement. Again, think of the question mark as if and the colon as else. So you evaluate some expression. Hey, if it's true, do this. Else, do this. Now this ternary operator, this nested ternary operator, has another statement. If speed, that gets evaluated. If speed is less than 0, meaning it's negative, non-zero, if it's negative, strictly negative, then we're going to do what follows the question mark, and we're going to return reverse to the direction. Else, we're going to do what follows the colon. We're going to return a 0, because that's all it would be at that point. If this is checking, hey, is speed negative? If it's less than 0, well, if that's true, it's reverse. Otherwise, the only other thing it can be is 0, because if it was greater than 0, forward would have already been returned. So this is confusing. It would have been simpler probably to do something like, just 1 second, my computer seems to be thinking. It would have been simpler to go something like if, motor state equals true, and even that's more verbose than it needs to be. You could just go with motor state, that's going to evaluate true or false. If that's true, then do a serial dot print line, motor on. And then else motor off. That would be more clear. So that would accomplish the same thing as this line of code. These are identical. This is more code, more lines of code for sure, but it's arguably simpler to understand, right? If motor state is true, output this, else output this. This is more complicated. It takes a little more brain power to kind of figure it out and parse through what it means, as opposed to this, it just kind of pops out at you. But again, this is more lines of code. Even if you take away the unnecessary braces that I've added, because again, they're just a single thing, you could, that's less lines of code for sure, but still more than the one line. Even if I put these on the same line, but arguably at this point, this is now more confusing when things are on the same line. But even then, it's still 2 lines of code compared to 1. So again, I've sacrificed simplicity and maybe clarity in this particular case for this. But again, it's for educational purposes. So anyway, this is just setting basically the motor state to true or false and the direction. And then if there was a state change, that's when I want to print the state changes to the serial monitor. So if motor state is not equal to the last motor state, then I'm going to output to the serial monitor motor on or motor off. Again, going to be decided by this ternary operator. Is motor state true or false? If it's true, do what follows the question mark, output motor on. If it's false, do what follows the colon and output motor off. And then just update last motor state to whatever the current motor state is. Then here, if motor state is true, meaning if the motor is on and the direction is not equal to the last direction, meaning there's been a state change, then I want to come in here and and evaluate. If the direction equals forward, I'm going to put forward to the serial monitor. Else, if it equals reverse, I'm going to put reverse to the serial monitor. So in this case, I did go the route of clarity and simplicity over doing another ternary operator like this, which I could have done. Then I update the last motor direction to direction again. And then if the motor is on, I do all this stuff, which is set the motor direction to whatever the direction is. Again, this time it can be 0 as a direction. And then I call the analog rate function, passing into the PWM pin a speed that's the absolute value. Again, no negative values are allowed to be passed to a PWM pin. It takes values from 0 to 255. So we call the absolute value function. And then same with the set color, which uses PWM to the red, green, and blue LEDs. So I set that color based on the speed. Else, meaning if motor state was false, meaning the motor's off, we just call the stop motor function. No change in the set motor direction. Again, I already had an else for if a 0 got passed in here. It just, the code was never reached before because, again, my original spin motor function only ever factored in forward or reverse. It only ever passed forward or reverse into the set motor direction. There was never a 0. But that being said, I never changed this code. This always existed. It just never got reached. Again, I've commented out the stop motor function because I've changed that. Now you can see that I've only added one line of code, this one. But sometimes I just comment it out so that you can see that the change. But as before, I still do an analog write to the PWM pin of 0. So basically I'm just stopping the motor, which is why the function is called stop motor. And then I'm still setting the LED color to full red and 0 green or 0 blue, so full red, full stop. I do that. The only line of code I added is the set motor direction to 0. I'm passing in 0 because I've made that change. No change in the button functions, no change in the RGB LED functions. Really no change here. So this is the display mode message function. I'm going to try to be quick because this was meant to be a quick add-on video and you guys are going to be, this is a full-length movie at this point. So display mode message, it takes in a mode, meaning an enum type, and basically it just compares, it checks the in the array, that Boolean array I have, it checks if it's false, because if not false is true, so that Boolean not. If it's false, meaning it hasn't been displayed already, then yeah, I'm going to come in and I'm going to display it. Whatever mode it happens to be, again, the enum types evaluate to menu mode, switch direction mode, button mode, photoresistor, and enter mode. Depending what enum got passed in, I'm going to output the appropriate message to the serial monitor, and I'm only going to do it if this was false, meaning if the value stored in the array for that particular Boolean flag was false. If not false is true, I'm going to come in here. I didn't mean to do that. And I'm going to output that. And then I'm going to set that particular flag to true so that I won't output it again until I leave that menu and come back. And then I'm going to reset all the other flags to false using this for loop. Again, as long as I is not equal to mode, which it'll only be equal to mode for one of them, this one, I'm going to set all the other flags to false. No change to any of these functions, no change to any of these functions from before. So I've commented a lot of functions, so I did have some issues that I ran into with prompt user for speed. And so I've just kept commenting out the code, kept making minor tweaks. But I'm going to try to wrap this video up, but I'm just going to let you know the quick issue that I had was with the input. So I was using serial.parseInt to read the input as an integer and assign it to speed. And the problem was that every time I was toggling into the mode that allowed me to enter speed, I'd enter whatever speed and it didn't matter. I would end up toggling to the switch coding challenge mode, but the motor would be off, and then it would be off, it would persist and be off as I toggle back through the different coding challenge modes. And what was happening was, because I'm using serial.parseInt, which reads an integer from the input stream, but if the stream was empty or there was no valid number provided, the serial.parseInt function defaulted to 0. So this was always assigning 0 to speed. And it was happening right away because, again, the code happened so quick that as soon as I entered the mode where I got to enter a value, it was reading the serial monitor, there was nothing there, but it was still coming in here because there's technically, a 0 by default, like it was still getting in here. And then it was reading it as a 0, which is a valid input. It's a valid speed because this speed accepts negative 255 to positive 255. So again, it was jumping out of the loop because it was setting this flag, which is how we stay in the loop, or how we exit the loop rather. It was setting the flag to true. It was doing all the stuff that allowed me to get out of that particular mode, but the speed was always 0. So long story short, the solution was for me I needed a way that the function would only process input if the user actually typed something. And how did I solve this? I used serial.readString until next line. I assigned that to input, and then I found some sort of clever solutions on Google and Stack Overflow and stuff that basically once I read something in, then I compared the length of the input. This is like just a different way to do it. Input.length. This would be the same as if like this was a string. It is the string input. So I'm testing the length of the string. Is it greater than 0? Meaning, is it non-null? Is there an actual value? Because that was my problem before. If there's an actual value, then I convert that string to an int and check to make sure it's not equal to 0, or that the input that got put in actually was the character 0, meaning it's all right if the character wants the speed to be 0. That's fine. That's valid input. But I need them to type in the character 0. I don't want it just to be what parseInt was doing, which is just accepting null string or no value as a 0. So long story short, then I would convert that input, assuming there was input, it was greater than 0, the length of the string. Assuming there was input, I still sign that to an integer, and then everything else is the same. All my validation is the same as before. So again, that was basically the issue I had. Again, the video's getting a little long, so I'm being quick. But basically, when I did some of this switching up, I had the issue where parseInt, because by the nature of parseInt, by default, it reads streams that are empty as 0, defaults to 0, or non-valid numbers as 0, which was causing me to always have a speed of 0 and just exit the function. So I had to fix it by using serial.readString until next line, which allowed me to basically check that, make sure the string wasn't empty and actually contained valid input. And that's pretty much the end of it. So thanks for watching. I know this has been a long video. This was actually only meant to be a quick live demo after, and just quickly talk about my coding changes, and it's already a half-an-hour video in addition to the hour and a half you've already watched. So if you have watched to the end, thanks for watching for the past 2 hours, and hopefully you learned something. If you have any questions, post them on the course forum and I'll be happy to answer them. Thanks.